let's talk a little more today about some solar activity here, and then we'll try and get that wrapped up and talk about what that means for what Earth looks like. If you remember, we kind of wrapped up last time talking about stars, the idea that stars were taking hydrogen, fusing hydrogen together to make helium. And we talked about the fact that stars kind of come in two basic sizes, kind of a medium-sized star, which is what our sun is. It's a star. And we talked about how that would go through its running out of hydrogen fuel stage by going through the red giant phase, finally shedding the burned out husk of that, and all that would be left would be the white hot kernel of the sun, and that would be the white dwarf. And eventually, with no more fuel to burn, that would simply cool off and wink out, and that would be the end of it. Our sun's going to do that someday. Our sun is about halfway through its life. And we know that our solar system started about 4.5 billion years ago. So we've got somewhere near 5 billion years still to go before our sun goes through this phase. Yes?
Can you get those extra lights put up? I think they usually aren't.
Well, they're on, but they're not real bright. Let's see if they're turn them up a little. Sure. Oh, there we go. Okay. Yeah, we're having a little trouble with this light switch. Doesn't seem to want to behave itself. Yes, sir. This building was built in 1972, and it's all the original light switches, and then these slider dimmers, and there are three switches controlling these lights, so they're having no problems. So we have to do a little revamping, I think. Okay. So that's kind of what's happening with medium-sized stars, and our star, probably in about 3 billion years from now, will start to cool off enough as it starts to run out of fuel that the solar system's pretty much going to freeze up. There won't be any running water on Earth anymore. And by about 4 billion years, Earth will pretty much have gotten toasted in the red giant phase. And by about 5 billion years, the red giant phase will have obliterated our solar system. And at that point, we can't just move out to Mars to find a cooler planet. We're going to have to be in a whole different solar system. So at the rate we're discovering things and able to do things, our space program's pretty important as a step to save civilization eventually for 4 billion years from now, if we live that long as a species, because we'll need to move solar systems in. Okay. The other size star is a giant, supergiant star. And being a big star is great, but it comes at a price because you have to use up a lot more fuel a lot faster. So it's burning hydrogen just like crazy. And some of this hydrogen that's in the star, it's kind of helping to prop the star up. It's kind of holding the matter apart. So as you use this hydrogen up, you're losing that propping ability. And now, as the star just gobbles up the last of its hydrogen, the star just basically starts collapsing on itself. That hydrogen isn't there to keep it inflated, essentially. And as it starts to collapse, the pressures go up, temperatures go up, and the star tries to pulse, but instead, things are just increasing so quickly that it just explodes, just blows up. This kind of a star is what we call a supernova. And the ultimate fate of a supernova is it either becomes a neutron star or it becomes a black hole. This is the Crab Nebula. You can see it in the sky now. It was first witnessed in 1054 AD by Chinese astronomers. And this is a supernova. Essentially, the light of this exploding star is still reaching Earth. It's traveled across space at the speed of light, and it's still coming toward Earth. Now, remember we started building the periodic table as the stars converted hydrogen to helium and more complex elements. But if you get up to iron, that's atomic number 25. Right now we've got, I think, 140 some elements. Most of the ones after 100 are man-made, essentially, make them in atom smashers. And they don't last more than a nanosecond or two. But after the complexity of iron at atomic number 25, it's pretty tough for a star to make that complexity. So iron's about as high up the periodic table as we get during a star's normal life. But in these supernova explosions, the pressures are so high, the temperatures are so high, that in that explosion, we make all the rest of the periodic table, all the other complex elements with atomic numbers higher than 25. And it takes about 30 seconds for that to happen. So supernovas are important. These big giant stars need to be happening to make all these other complex elements. So, clicker time. What do medium stars become? Supernovas, white dwarfs, red giants, or both B and C? Give you 20 seconds here. Okay. Everybody wants to pick B and C. Okay. Well, if you pick B or C, you were partway right. If you think about it, medium star, the first thing it does is it goes to the red giant phase as it's pulsing, right? And then after it's done that, and it's on the very last little bits of just winking out, all that's left is that little white hot kernel of the sun, the white dwarf. And then it simply cools down, no longer luminesces, and then it becomes what we call a black dwarf, which is kind of like a little lump of charcoal briquette sitting right there, the remnants of the white dwarf. So, B and C, so D answer is the correct one. Okay, so let's kind of look at our solar system. We're a subset of our universe, right? And our solar system, we think, began about somewhere at the very beginnings, about 6 billion years ago.